welcome back. We're going to be discussing about pass transistor logic. Let's have a look. We have discussed pull-up and pull-down network and how we can design the CMOS circuits in previous lecture. So just to remind ourselves here, the pull-up network job is to pull the output to VDD, and pull-down network will pull down the value of our output logic level to ground. Okay, so pull-up network, pull it to VDD, pull down to VSS or ground. Okay, now we also have discussed about PMOS in a configuration of the pull-up where when the gate is connected to 0, the output is pulled up to strong 1. That's characteristic of the PMOS we have discussed. We have also discussed similarly the characteristics of nmos, okay, where the gate is connected to VDD and one terminal is connected to ground. If we take the output from another terminal, that will be pulled down to ground. And we have formalized few equations that what if gate is connected to 1, the output which we represented with the pull down network output will be pulled it down to 0, logic level 0 or ground. Okay, and we have also discussed one NAND example. Okay, so NAND example, right? We constructed the pull-up network in parallel PMOS configuration. Okay, and that connected pull-up network is connected with pull-down network, and pull-down network we have nmos in series configuration. Okay, we have discussed in previous lecture. Those who have not watched the lecture on the CMOS circuit design, I would recommend you to watch that. Okay, now what if we have to design an AND gate? So we can simply invert the output of this NAND gate. Okay, put an inverter out and then get the output. Okay, or more formally, we put an inverter circuit, one PMOS and one nmos. Okay, and take the output from one of the terminal. All right. What if we wanna count the number of transistors? For this particular example, let's have a look at number of transistors. Okay, so we have, let's keep it counting. We have 3 PMOS, and similarly we have 3 NMOS connected together. Remember that this is a very simple example of a NAND gate. More complex example using the CMOS technique, this pull-up and pull-down technique for XOR, XNOR, or complex logic gates will have more transistors. Similarly, one can design half adder, full adder, more complex logic circuits using this technique, pull-up and pull-down network, right? So those we will be discussing some point in future, but the basic fundamentals are similar for designing the CMOS circuits. Okay, we have discussed about how to design the circuits in previous lecture. So is there any way we can reduce the number of transistors in this simple example of an AND gate? Think about it, right? Can we design a circuit in some other way so that we have to use less transistors? Okay, the more transistors we have, right, we have to deal with more area of the circuit, right? And one approach, right? Now these are smaller, standard cells, right? So the people, right, folks who design standard cell or libraries, right, they try to optimize the standard cells. So lower area, right, will consume lower power, right? So various other factors which will not be covering here. But in this lecture, the idea is to cover the basic concepts. Okay. Can we reduce transistor count? Let's have a look how we can use pass transistor logic approach. So first, let's understand, go back to the basics, PMOS, right? So in PMOS configuration, we have already seen it that when the gate is connected to ground, and one of the terminals is connected to VDD, this produces a stronger one. What if instead of VDD, we connect it to another input, let's say logic level, right? Let's say another secondary input to the circuit I2, okay? And one input I1 is connected to the gate, good. And we are taking the output of this circuit from another terminal. So very simple, same configuration. So what will happen in this situation? When I1 is connected to 0, this PMOS will be conducting, right? So electrons will be flowing from one terminal to another terminal, current flow will happen, okay? So this will pull the value of this other terminal to the logic level of I2, okay? Or the input I2 logic level, whatever voltage is here, pull it down to this node, okay? So we have formalized another simple concept regarding PMOS. Similarly, we can see the nmos. So one input is connected to the gate of the nmos, and another input of the circuit is connected to one of the terminal of the nmos. Okay, and if we take the output from another terminal, and we have already seen that when I1, or the input which is connected to the gate, will go to logic 1 or high, this output will be pulled down to the logic level what is I2. Okay, so this we have seen. So what if, right, so we can have this configuration of PMOS and NMOS. So what do we see here? That for PMOS, when the gate is connected to ground or logic level 0, the output get pulled to the voltage or logic level I2. Fine details of what will be the voltage level, that there are equations we can have a look at later. But the idea here is that how the pull up and pull down are working when we connect the gate and terminal to the primary inputs. All right. Now we can formalize it a little bit more, that PI, okay, let's say PI is a control for input which we are connecting from one of the terminal. Okay, so what it means that imagine that this is a control, means this is a valve. So once this valve is on and off, the water will flow, right, from I to F. Think about that analogy, water analogy. And PI is some kind of a control switch or valve. When it is on, water will flow. When it is off, water will not flow. For the case of the PMOS, when this control PI will be at logic level 0, output will have logic level, what is logic level I. And this transistor becomes a pass transistor, in other words. Okay. Similarly, we can formalize for NMOS that on the NMOS gate, we have a valve. And once this valve is on and off, electron will flow through this pipe. Or in water analogy, water will flow when the valve is on. And when the valve is off, water will not flow. Okay. So when the pi is 1, f output will tend to take the voltage level of what is at the another terminal we are representing with I. So what we can say for the PMOS, when the control is at logic 0, this is conducting. And for NMOS, when the control PI is at logic 1, this NMOS is conducting. So in other words, the valve value, okay, or the valve or switch, water switch or water valve is on when PI is 1, logic high for the NMOS. And for PMOS, it's the other way. So these transistors are actually passing the value from one terminal to another terminal depending upon the control applied at the gate. All right. So why we say for PI, for PMOS, if the gate control is 0, F will be 1, provided that logic level I is high, okay? And it will produce a stronger one. Similarly for NMOS. So this is nothing but a pass transistor logic, okay? Where the control, right, control value, we are saying at PI, or nothing but the control for the input I applied at the gate of the transistor. So remember this simple concept, and this becomes nothing but a pass transistor logic. Okay, good. These are just in perspective to remind ourselves, formalize the equations. One can say that, okay, what if, right, PI for NMOS is 1, okay? So what will be happen at the output? It has been found that this produces a weak value at the, or weak voltage level at the output. So it's like when the PI or the gate control is off, means that it's 1 for PMOS. Water is not flowing, but it might be like few drops of water will reach from I to F, and those will not be significant to say that the F has reached to the same voltage level as I. So it's representing weak, okay? Now similarly for NMOS, when the PI is 0, F, output function F, has a weaker value of I, okay? We prefer to use NMOS for various reasons. First reason, one can say that the mobility of the carriers. For PMOS, it is holes, and for NMOS, electrons, which are faster than holes. So it will be a faster switch for NMOS. And the area advantages to PMOS is roughly double than the NMOS, right? So for various reasons, NMOS are preferred. Okay, good. Now let's see an example of an AND gate. Good. So we have this AND gate, and we have this truth table for the AND gate. Okay. What we can say from this truth table is when I, one of the input, is 1, then output depends on second input. Okay. So that's very good, because now we have at least cover half of this truth table, and we know that, right, if we use the NMOS, right, and we connect the gate of the NMOS to one of the primary input, right, then we are covering this red bounded box condition in the truth table. Okay. All right. Good. So here, as you can see here, we connect the gate to one of the primary input I1, and if we connect the I2 secondary input to one of the terminal and take the output from another terminal of the nmos, then F will produce, right, the value what is on the I2. If it is 0, value of the F will be 0. If it is 1, value of the F node will be 1. Okay, so in other words, I1 tends to 1, F will become I2. Good. So we have seen the we have covered half of the truth table. Now let's look at the second half of the truth table. So in the second half, we clearly see that irrespective of the I1 and I2, provided that I1 is 0, okay, the F output is 0. Okay, so what we can say here that what if we connect the gate of the nmos with the inverted value of the I1? Means what if we put an inverter and then inverted value we connect it to the gate, okay, of this transistor, and then one of the terminal we connect it to the ground, then we will get a 0 value, okay, which means that the above half we are covering. And it doesn't matter because once we have, right, as per the truth table, it doesn't matter what is the value of the I2. If I1, which we are considering here, is 0, and one terminal we are connecting with the ground, it will produce 0. So that's good. That's good. We got at least configuration, right, for the circuit, how we can connect it. Okay. Now remember that pull up and pull down network joined together, then if we can connect both terminals together, then we get the desired output of the AND gate. Okay, good. Now I1 bar was nothing but the inverted value, so we put an inverter. More formally, we put a circuit of the CMOS circuit for the inverter, and output we connect to the gate of the nmos. Okay, so this gives a simple circuit for AND gate. All right, we can connect it further, right? So that completes the circuit of the AND gate. Now, irrespective of what characteristics of this circuit and all, this is a basic mechanism, right? How you can think about developing circuits using the pass-transistor logic concept. Now let's analyze the circuit. So when I1 is 0, okay, when I1 is 0, what will happen? This PMOS will be conducting, right? So whatever value is here, this is an inverter circuit, okay? So inverter circuit, this value will come here. So we assume that this value will be at the logic high, VDD. And that is connected to the gate of the nmos. Okay, so this will be conducting, and the output, right, will be pull it down to ground. Good. Now let's look at the another branch. I1 is 0, right, and here we have another nmos, and this nmos, right, will be switched off. The gate is at 0. So technically it will produce a weaker value at the another terminal, weaker value of the logic I2, which is so weak that this stronger one will take over and will get logic 0 at the output. Okay, so what will be the value, voltage value we can approximate? We can approximate the value as the voltage level of I2 minus the threshold voltage of the transistor. Okay. The characteristic equation you can look in the textbook, right? And that value we can safely approximate is very near to the voltage level of the I2, right? Good. Very, very good. So now let's look at how many transistors we have used here. So we have used one PMOS and 3 nmos transistors in whole circuit. We have total four transistors. And if we don't use the pass transistor concept, as we have seen in the CMOS circuit case, we will have to use 3 PMOS and 3 NMOS. Okay, so these 3 PMOS connected in parallel configuration, right? So this is an AND gate, right? And then inverter, right, becomes an AND gate, right? So these two transistors are in parallel, these two are in series, and then followed by an inverter. Now if we compare this circuit with our pass transistor circuit, so we are definitively achieving a smaller circuit if we use pass transistor concept. So from the 6 transistor to 4 transistors using pass transistor logic. So what we can say, lesser transistors, good. Lesser physical capacitance, and lesser energy to charge up a node when we have, right, as we already said that pass transistor logic has less physical capacitance, right? And lower power circuits we can create using the pass transistor logic concepts. But we got to be a bit careful as we have analyzed the voltage, right? So when I is 1, this NMOS will be conducting, right? And the voltage level to produce the logic high will be voltage, what is at I2 minus the threshold voltage. And you may also include the bias here, bias voltage and all. So essentially, the voltage level at the output, it will not be the level of the VDD or level of the VI2, but we're very close. So we may need an extra circuit at the output to bump the voltage level to logic level high when I1 is 1. Okay, or in other words, level shifter you can use, or you can use an buffer, right, inverter, right. Good. So here in this example, I'm just saying that we use a buffer, right, or level shifter, right. In other words, right, low power techniques, people use level shifters, right. So in simple way to say, extra circuit is needed at the output to scale the voltage. Okay, so that's a little bit drawback of the pass transistor logic, other than the major advantages here. Right? Now, the one important considerations when designing the logic using pass transistor logic is that when we do cascading, so this cascading is actually not good. This is not good. Means that if we connect one of the terminal, right, to the gate of another transistor, a pass transistor, we will have voltage drop at the final output, right? And that voltage drop will not be will be very significant voltage drop, right? So it will be like as if this in this circuit, example circuit, we expect to have F to reach to VDD, right, when I1 is 1. Well, what will happen, the value of at the output of the F will not be VDD, but VDD minus the threshold voltage for this transistor I1 and threshold voltage for the transistor I2 and some bias voltages and extra. So this essentially will be a pretty low voltage, and depending upon how many cascading transistors you are putting, you will have to develop a bigger circuit to pull the value to a logic high. Essentially is not right helping us. So this configuration, right, where you will have to connect the terminal of the pass transistor to the gate of the another pass transistor is to be avoided. Okay. So what we can do when we have to cascade it, we can cascade in this manner where we can connect the terminal to terminal. So terminal of one pass transistor is connected to terminal of another transistor, pass transistor, and the gates will be connected to primary inputs. So that's we have to keep in mind. Okay. Or in other words, the gate should have a good value, or VDD, or right, high logic, high value. Okay, good. This is a good way to cascade it if we have to cascade that. Connect terminal to terminal and primary inputs to the gate of the pass transistors. All right. Thank you very much, guys. If you like, subscribe, share with your friends, and press the bell icon for notifications. That helps to notify you once when I upload a new lecture. Thank you once again. Leave your comments below, and if you need any other topic to discuss, please feel free to leave a comment.